Now I come to the first lecture where we have found out the Fourier series expansion of the function fx equal to x square in the range -pi to pi, and ultimately we come up with this Fourier series now sometimes given in the questions that find the Fourier series of the function fx is x square, and hence prove that sum of some series equal to some number. Now how to deduce those series, that I am going to talk. Now put this one as the number of the equation and substitute x equal to 0 in 1, then we will get 0 equal to pi square by 3 4 minus 1 to the power n by n square, and cos of 0 1. Now if we take out this pi square by 3 left hand side and divide by 4, so it will be minus pi square by 12 sum of minus 1 to the power n factorial n. Now if I expand this part, then it will be minus 1 by 1 square plus 1 by 2 square minus 1 by 3 square plus so on. Now multiply minus 1 both sides, then we get pi square by 12 equal to 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus so on. Now you see, this is a series, alternating series. In the chapter sequence series, we only can say whether this alternating series converges or diverges. Now we are seeing the value of the series. So this series converges, alternating series, and the value of the series is pi square by 12. So this is one of the byproduct we can say for the Fourier series. Okay. Now give equation number 2 for this equation. Now again we are substituting x equal to pi in the equation 1. Then we'll get pi square equal to pi square by 3 plus 4 minus 1 to the power n by factor n square cos of n pi. So this is minus 1 to the power n. So this is pi square by 3 4 sum of 1 by n square. as minus 1 to the power n, and minus 1 to the power n will be minus 1 to the power 2n, and that is 1. Now take out this pi square by 3 in the left hand side. So this will be pi square minus pi square by 3, therefore 2 pi square by 3, and 4 is there, so it will be pi square by 6. So this is pi square by 6 equal to sum of 1 by n square. So this is 1 by 1 square, 1 by 2 square, 1 by 3 square, so on. Now you see, this is a P series, and P series converges for P is greater than 1. Here P is 2, therefore this is converges, and this is the value of the series. Give the name of equation 3. Now you see, if you add 2 and 3, then all the terms that is in the even position of the series, that will be cancelled out. Only odd terms will be remain, twice of the odd term. So then again we will get a series, and we will find the value of that series. Okay. Now what happened sometimes in the exam, it's given that find the series of pi to the power some 4 by 90 equal to 1 by 1 to the power 4, 2 by 2 to the power 4, 3 by 1 by 3 to the power 4, and so on. So in that case, if we add up these 2 and 3, we cannot do it. So what we will do in that case, there is a theorem called Parseval's theorems, also it's called Parseval's identity. I am now going to discuss that one. It is sometimes called Parseval's theorems, also known as Parseval's identity. So let's state what is that Parseval's theorem or identity. Suppose you have given one function fx defined over some interval, and that function satisfies the Dirichlet condition. Therefore we can expand that function by a Fourier series. So let's that some function fx defined on say minus L to L, and also satisfy Dirichlet condition. Then it can be approximated or expanded by Fourier series. Then fx will be a0 by 2 plus an cos of n pi x by L plus bn sin n pi x by L Now a0, an and bn are the Fourier coefficient. Then what the Parseval's theorem is saying that then Parseval's theorem saying that 1 by L minus L to L square of the function fx dx equal to a0 square by 2 plus sum of an square plus bn square. Okay. Now I will explain one example and show that using that Parseval's theorem identity, how we can find some series which contain the terms like 1 by 1 to the power 4 plus 1 by 2 to the power 4 and so on. So let's have our original first example of the Fourier series where the function fx was x square and range was minus pi to pi. We apply Fourier series for that Parseval's theorem for that function. During solving this equation, we find out that a0 is 2 pi square by 3, an is minus 1 to the power n by n square and bn is 0. Now we substitute this in that Parseval's theorem or identity equation. So it will be then 1 by pi minus pi to pi fx is x square is a square, so it is x to the power 4 dx. a0 is 2 pi square by 3, so 4 pi to the power 4 by 9 and an is 4 minus 1 to the power n by n square, so this is 16 sum over 1 by n to the power 4. Now integration of this one is over symmetric region, so therefore it will be 2 by pi to the power 5 by 5, and this side it will be pi to the power 4 by 18, 2 pi to the power 4 by 9. And this is 16 sum over 1 by n to the power 4. Okay. Now this side it is 2 pi to the power 4 by 5 and 2 pi to the power 4 by 9 that side. If we take out that one this side, So it will be 2 into 4 pi to the power 4 by 45 equal to 16 1 by n to the power 4. So this implies pi to the power 4 by 90 equal to sum over n to the power 4, and this is nothing but 1 by 1 to the power 4, 1 by 2 to the power 4 plus 1 by 3 to the power 4, so on. Therefore, this is one of that series that contain the terms like 1 by 1 to the power 4, 1 by 2 to the power 4, 1 by 3 to the power 4, and so on.